Hello, good evening, everyone. To those, good evening, thank you. To those who are joining for the first time, okay, so this week is actually week 6. So we have these weekly sessions where we solve some problems similar to your assignments and look at the methods behind those problems. And we have these sessions every Saturday 7 to 9 p.m. And my name is Akhil Reddy PKT. I am a PhD scholar from IIT Madras. So please mute yourself as default, and if you have a doubt or question, you can unmute yourself and ask. Okay. And these live sessions will be uploaded to YouTube with this playlist name, Machinery Fault Diagnosis and Signal Processing Live Sessions. And the links will also be uploaded in a sheet which is already shared in the NPTEL website, the course website. Okay. Yeah. So let's begin today's session. So we can have some interactive sessions. So the first question for today is random error can be reduced by taking average or maximum or minimum of the measured results. Does anyone know what is random error? You can unmute yourself and answer if you know the what is random error. And what should be the answer for this question? Yes. Yes, correct, Samir. The answer is average. But what exactly is random error? So, yeah. Yes. So yeah, yeah. So let's say if everything is ideal, when you are measuring the signal should look, let's say, something like this. But because of okay, or because you are sampling at some specific time, it should look like this, perfectly every time matching. But because of as noises, what Samir mentioned, you might have data points somewhere, something like this, because of the noise in the system. So if you take average of this, you will actually again get the real answer. You will be close to the real values. So that is why when there is random error, it's better to take average of the measured results. Okay. I hope this is clear. So random error can be reduced by taking the average of the measured results. Okay. Yeah. So next question. Calibration helps reduce which kind of error? Random error or bias error or quantization error? Can anyone answer this question? So we know what is random error. It is caused by this external noise. So even if you calibrate the instrument, you will still have this external noise, right? So whether you calibrate it or not, that will always be there. So it is not for random error. And what is quantization error? So in our previous weeks we discussed it, right? If the signal is less than the least count or the resolution of your instrument digitization, then you won't be able to pick up that signal. So the error occurring due to that is the quantization error, because when you are converting analog signal to digital signal, you will only be able to look in terms of the resolutions. So let's say you will only be able to track 0, 1.25 millivolt, 2.5 millivolt, 3.25 millivolt, like this. So the in between data you won't be able to have access to. So because of that, the error arising due to that is the quantization error. So in that also the calibration doesn't help. So what exactly is calibration? Let's say you have a simple mercury based thermometer. So almost everyone would have come across that from your childhoods. So it has a mercury bulb at the end, and there will be temperature markings here, right? Let's say 20, 30, 40, 50, 60, 70, like this. Okay, and 10 and 0, let's say. Now let's say uh, if this instrument is not calibrated. So for room temperature, let's say 30 degrees, you know it's around 30 degrees, but this mercury is always giving somewhere around here 40 degrees. But you know that it is supposed to give around 30. So then what you do is you need to calibrate this thermometer. So for the temperature, the best way to calibrate it is take a ice bath. So ice bath should always be at sea level at atmospheric pressure 0 degrees. So what you do is you place this thermometer in the ice bath and see whether it is giving 0. Let's say in in ice bath it is giving 7 degrees. Okay. So then what you do is you change the amount of mercury in the bulb, or you can adjust the dia of this rod in which mercury goes up, so that in ice bath it gives perfectly 0 degrees. Okay. So basically this is calibration. So I explained it for thermometer, but if you are doing this for any instrument, let's say an accelerometer or something like that, so that is the calibration. And this bias error is, it gives a constant extra or a constant difference between the actual value and the measured value. So let's say it should give 20, but it always gives 30, and when it has to give 10, it always gives 20. So this extra difference 10 is the bias error. So this you can reduce by doing the calibration. Okay. So calibration helps reduce the bias error. Is this clear? Okay. Yeah. So it's a slightly big question. We have two sensors A and B. They give the following readings. So the readings are given here, but the output should be 10. So you also know from an instrument which works correctly that the output is 10, and we know the readings of A and B. What can be said about A and B? So yeah, okay. So we are asked to comment on their precision and accuracy compared to, in comparison between A and B, and we know the value should be 10. So the readings of A are 12, 12.1, 11.9, 12.05 and 12.07, whereas for B it is 10.2, 10.5, 11, 9, 9.5, 9.8. So can anyone answer this question? In between A and B, which is more precise and which is more accurate? I'll give you a minute to think about it. Okay, A is more. Okay, so the answers are B is more accurate than A and A is more precise than B. Okay, so can you give your reasoning for that? Yes, so the readings of A, they are closer to each other than B. To each other than B. And readings of B are far away, but readings of B are much closer to the actual value than A. Closer to each other than B, or mean difference, as you said, low. So A is more precise than B. But the average of A is around 12 and the average of B is around 10, I guess, close to 10. So B is more accurate than A. Okay. So for visualization, I'll give you just a simple example. Let's say this is the dead center bullseye. If all the values are like this, so here this is more precise, right? And this one is more accurate. Okay. Yeah. So this can help you in visualizing this accuracy and precision. I think this is clear. So if all the readings are the difference between the readings is very small, then that is more precise, and if they are closer to the actual value, then they are more accurate. Okay. So is there a way that we can make A more accurate? So if you calibrate A, basically reduce the bias error, then you can actually make it both accurate and precise. So that's what actually happens in instrumentation. Okay. No, no, no. Yeah, two options. Yeah, this answer has two options. Both are correct. Yeah, this is a multi-option question. Yeah. Okay. So which of the following needs a dynamic measurement type sensor? So there are two types of sensors, static and dynamic. So static is used for the cases where the whatever you are measuring doesn't change so much with time, and the dynamic for the cases where the signals change a lot with time. So in these three, which one we should use dynamic measurement type sensor? Temperature of a room, vibration of an engine, air pressure at sea level. In general, vibration of engine is much more dynamically varying phenomena, because the frequencies which you would get are 100 hertz, kilohertz and all. But temperature of a room doesn't fluctuate that much. It's around 20 to 30. In general cases, it's always room temperature around 25. It fluctuates, but comparatively not that much. But the vibration of an engine oscillates a lot. And air pressure at sea level is almost very close to 1 atm. So in those cases, a static sensor is good enough. But for the vibration of an engine, you need a dynamic measurement type sensor. Okay. I hope this is clear. Static for cases where the measuring physical value and dynamic Okay, yeah. Let's move to the next question. The natural frequency of a transducer is 1 kilohertz. For which of the following cases this transducer is not useful? So we were given a natural frequency of a transducer, and for which cases we shouldn't use this transducer. So for case 1, vibrations at 0.01 kilohertz frequency, vibrations at 1 kilohertz frequency, AC signal with 1 hertz frequency and AC signal with 0.1 hertz frequency. So where do you think this transducer is not useful? Why? Why do you think we shouldn't use it there? Yes, yes, exactly correct. So these transducers, we should always make sure that the natural frequency is far away from the frequencies which are actually in the physical measurements. If the frequencies are close, then you will have resonance. So the measurement would actually be much more than what it should be. So for example, let's say you have 5 volts at 0.1 hertz and 5 volts at 1 kilohertz. Okay, so a transducer of 1 kilohertz natural frequency for, so when you measure this, so it will show up as only 5 volts if you have this frequency difference, but in this case it might show up as 500 volts or very large number because of the resonance. So basically whatever you are measuring is kind of an input, and whatever is given by the transducer is an output. When you are in the resonance condition, the ratio to output input will be much higher. So because of that, you shouldn't use your transducers when you are close to the natural frequency. Be far away from the natural frequency of the transducer. So usually when you get this transducer from the manufacturer, they will give you a range for which frequencies you can use this. There is a question in the chat. So for valve trend, we measure valve lift with transducer for every cam rotation or RPM condition. Will that be come as static sensor or dynamic? If the RPM is changing a lot, let's say you are using a optical encoder or something to measure this rotations RPM, and if this RPM changing a lot in this sense, what I mean is, so when you switch on, the RPM actually goes from 0 to some certain value and then oscillates around there. In real systems, RPM is never a constant value at 500 RPM. It could actually go from 501, 502, and again when you switched off 0. So it's better to have a dynamic measurement system there. I hope that is clear, Sachin. Okay, thank you. Next question. Determine the dynamic range of a transducer which can measure a bipolar signal of 50 volts. I hope the last question is clear. Okay, next question. Determine the dynamic range of a transducer which can measure a bipolar signal of amplitude 50 volt provided the resolution is 1 millivolt. Okay. So here the question is about dynamic range. So have anyone come across the formula for the dynamic range yet? So for a given transducer, this is the formula for the dynamic range. So 20 log 10 range by resolution. So what is the range here? It is mentioned a signal of amplitude 50 volts. So will the range be 50 volts? Here there is one more important thing that you should notice. They said it's bipolar. Bipolar with amplitude 50 volts. So that means it would be something like this. Amplitude 50 volts. Because it is bipolar, so it has both positive and negative. So the range would be actually 100 volts. Okay. And then the resolution is 1 millivolt. So that would make the dynamic range 20 log 10 100 by 1 millivolt. So 10 power minus 3 10 power 5. So 100. So is this clear? How to measure, determine the dynamic range given the signal amplitude and the resolution. Okay, it's just the 20 times the logarithmic of the ratio of range to resolution. Okay, yeah. Let's look at the next question. Yeah. So determine the dynamic range for a transducer which uses 8-bit storage. So no other information is given. It just says the type of storage system that is used, and we are supposed to calculate the dynamic range. So can we calculate? So what do we need to measure the dynamic range or determine the dynamic range? We need range by resolution, right? So, but here range is not mentioned and resolution is not mentioned, but the storage type is mentioned. So, does anyone remember how these three are related from our previous weeks for a given storage system? I'll give you a minute to try to remember. Range, resolution, and the type of storage. Exactly, exactly. Thank you, Muthu. So resolution, we already know that it's for a given storage system based on the bits type and the range you are measuring. Resolution you can estimate by range by 2 power n. Okay, n being the storage type. So here we need range by resolution. So that would be range by resolution is just 2 power n, right? Therefore, we can directly write the dynamic range is equal to 20 log 10 range by resolution as 20 log 10 2 power. Okay. So here it's given n is 8. So therefore the dynamic range is equal to 20 log 10 of 2 power 8. So 2 power 8 is 256. So this would be around 20 into 2.4, around 48, I think. Okay. So even though it looks completely odd because range and resolution are not mentioned, because they are related to the type of storage, you can still estimate the dynamic range just without any other details. Okay. So is this clear to everyone? How we got the dynamic range when it's only the storage type is mentioned? We need the ratio of range and resolution. So that is actually equal to the 2 power type of storage. So from that we can estimate the dynamic range. Okay. So let's move to the next question. Units of charge sensitivity for an accelerometer. Let's say you have a certain type of accelerometer where you can measure the charges. This is a charge sensitivity. You can measure only the charges. It doesn't give you the voltage. Let's say think of it like a capacitive based accelerometer, where you can the measurement will be in terms of charges. Because we set charges, it's not millivolt, it's not current amperes. So this is volts per acceleration. This is current per acceleration, but this is picocoulombs. So coulomb is an unit of charge, right? So this is the answer. Okay. So this charge sensitivity is something like for a 1 meter per second square acceleration, it will give maybe 1 picocoulomb change in the charge of the capacitor. You can maybe think like that. Okay. Yeah. Let's move to the next question. Which of the following instrument can be used to display acquired voltage as a function of time? So you have a transducer plus data acquisition system and then connected to a display where you are able to connect it to some system where it actually displays the acquired voltage. So what is that final instrument called? Amplifier, transducer, oscilloscope, none of the above. Yes, the answer is Ostroscope. Transducer is a sensor where you will just give the where it will just let's say generate a voltage for a given sensor or generate some kind of measurable thing, but it doesn't display anything. So oscilloscope can convert whatever that current signal which is passing through into a visual aid. So that is the oscilloscope. So that's the answer, and it's not amplifier which will actually multiply the, let's say, voltage and increase the magnitude, and transducer is for measuring. It's kind of like a sensor, so it's not the one used for displaying. It's you will actually see it in an oscilloscope. Okay, as a function of time, that voltage whatever it is coming. Okay, I hope this is clear. Oscilloscope is the instrument which is used to display the acquired voltage. Next question. Which of the following can be used for measuring displacement? LVDT, eddy current principle based proximity probe, capacitive probe, or all of the above? Okay. Yes, LVDT also. Yes. So LV you can actually measure with all these three. Their working principles are different and the ranges in which they can work is also different, and the frequencies that you can measure the displacements is also different, but all three can be used to measure displacement. Okay, so LVDT is a linear variable displacement something, forgot the full thing, but it can be used to measure displacement but at low frequencies. And eddy current principle based proximity probe, you can measure the displacement, and the capacitive probe also you can measure the displacement. So capacitive probe may work like these two. You actually need a metal based it works on metal based objects only, because in eddy currents, based on the distance, the amount of current generated in that metal object would be different, and because of that the corresponding magnetic fields generated and all would be different. So it only works in the metal based objects. Even the capacitive probe also works only in the metal based object. So let's say you have one plate and this is the object, metal object. So based on the distance and let's say all these are connected to the battery, the capacitance will change based on the distance between the plates. So that's how a capacitor displacement sensor could work. And even the eddy current one also, you need a metal based object only, because it has to generate currents inside the object. Okay, all these three can be used, so the answer is all of the above. Okay, I hope this question is clear. Okay, next question. Piezoelectric crystals can be used for measuring acceleration, force, both, or none of these two. Force? Yes. So piezoelectric crystals you can actually use for both acceleration and force. Yeah. So that's it. I think in this question, yeah, there is nothing more. See. So there is one more advantage of piezoelectric compared to other transducers, other material-based transducers. Does anyone know what is that advantage? For piezoelectric based transducers? I think we have that question coming. It's okay. Phototachometer is used to measure what? Rotational speed, temperature, force, none of them. Yeah, phototachometer. Yes. So yeah, a phototachometer or a optical tachometer is actually used to measure the rotational speed of the shafts in general, and this works with non-contact based system, and it's not temperature and force. Yeah. Okay. I hope you guys know this. In stroboscope, the rotational speed is detected by using xenon lamp that is switched on and off at with varying frequencies. Is that true or false? So does anyone know what is stroboscope? Okay. So you guys might have come across. Can you mute? Yeah. So you guys might have come across videos where you see the helicopter flying, but the rotors look stationary, or a hummingbird flying, but its flaps look stationary. So that happens when the shutter speed of the camera is same as the RPM of the rotor. So because of that, it looks stationary even though it's actually rotating. So this phenomena is actually used in this stroboscopy to measure the rotational speeds. Okay. So here using this xenon lamp that is switched at varying frequencies, at certain frequency it looks like the shaft is not rotating. So that frequency which corresponds to that is the actual corresponds to the rotational speed. Okay. So at other frequencies it looks like it's rotating, but at that particular frequency it looks like it stopped, even though it didn't stop. So that's how a stroboscope works, and the answer is true. In stroboscope, the rotational speed is detected by switching on and off the lamp at varying frequencies. Okay, is this clear? Okay, the next question. Which of the following can be used to measure temperature? A thermocouple, all of the above, yeah. That is correct. Resistance temperature detector and a pyrometer. Yes. All these can be used to measure temperature. So there is one more very useful one which can be used to measure temperature based non-contact one. Does anyone know what it is? A non, yes, infrared thermal camera. Yeah. So pyrometer is also non-contact based. So this IR thermal camera and pyrometer are non-contact based, and these are primarily used for high temperature measurements, because high temperature cases, if it is contact based, the sensor plus transducer itself gets very hot. So usually in high temperature cases, we use a non-contact based pyrometer or thermal camera. Okay. Yeah. Next question. Which of the below two can be used to measure both AC and DC currents? Hall effect sensor, inductive current sensor. Both AC and DC current. Yes, Muthu. You are saying something? Okay. Which of the below two can be used to measure both AC and DC currents? Hall effect sensor or inductive current sensor? Only one of these two you can actually use for both. So which is that? Okay, first let's look at the principle how these work. Then maybe you can have a better guess. So in inductive current sensor, you actually have an inductor based transducer. Inductor based transducer. So in which current type of current can an inductor work? Does an inductor work for the DC signal? No, right? So when you have two inductors, so if an AC current is passing through it, then it can generate an AC current in the other one also. So when they are close by based on induction, so inductive current sensor actually works only for alternating current. But Hall effect sensor works because when you have a conductive, let's take a wire, any conductive any conductive item passing through a changing magnetic field. passing through changing magnetic field will generate current inside it. Okay, so it works on this principle. So it works for either AC and DC. Both can create this changing magnetic fields. Okay, so it works for both AC and DC. Okay, so that is the Hall effect. Okay, now which of the following can be used to get the composition of the chemical elements present? Atomic emission spectrophotometer or atomic absorption spectrophotometer? Have you ever come across this previously? Okay. So in atomic emission spectrophotometer, you can actually only tell what kind of chemicals are present, but not how much they are present. So in atomic emission, you heat the whatever sample to very high temperatures, make them ionized, so that they generate light. So based on this light, that's why it's emission. You can actually tell each chemical atom or molecule will have a specific signal, specific wavelength at which it generates light. So based on that, you can tell which chemical it is. So you can only qualitatively tell if some chemical is present. Okay. But in atomic absorption spectrophotometer, you can actually tell how much of it is present. So it gives you a quantitative results. Okay. So if you want the exact composition of the chemical elements, then you need to use the atomic emission absorption spectrophotometer. Okay. Yeah. Next, which of the following two are useful for measurements at high temperature? Yeah. So let's say you have to use this accelerometer at temperatures of 400 degrees Celsius. Which one do you choose? Piezoelectric based one or strain gauge based accelerometer? Does anyone know what piezoelectric sensors are made of? Which kind of metal it is? Ceramic or metal or plastic? Which kind of the material are piezoelectrics composed of? Uh, yeah, semiconductor sensor, that is different, but what is the major material? Piezoelectrics are actually made up of ceramics, ceramic kind of materials. So because of that, they can withstand very high temperatures without showing any expansion or anything. Can withstand high temperatures. Okay, so when you want to do measurements high temperature, it's better to use a piezoelectric one. If you are using the strain gauge based accelerometer, the temperature actually affects the strains which you would get of the sensor itself. So it's useful to have something where temperature doesn't influence the readings. So it's better to use a piezoelectric based sensor. Okay. Yeah. This is it for this week. I'll just revise these questions once again. So our first question for today was how you can minimize the random error. So we saw that by taking the average of the measured results, we can actually reduce the random error. So random error can be reduced by taking the average of the measured results. The second question was to which errors you can actually reduce by using calibration. So we saw that if the values are constantly above some certain value, there is a constant added to each measurement, that is called bias error. So if you actually can reduce or remove that bias error by calibrating the equipment. So we looked at an example of simple mercury level based thermometer. So calibration helps reduce the bias error. Next we looked at two sensors, the readings from the two sensors, and based on how the readings are, the difference between the readings and how close they are to the actual output, we commented on whether which one is more precise and which one is more accurate. So if all the values are very close to each other, then that gives you the precision of the measurements. If the values are more closer to the actual value, then that gives you a measurement of the accuracy of the readings. Okay. So in this case, because the actual value is 10 and the readings of A are all around 12 point something, but they are very close to 12. A is more precise as the values of B are varying from 10 to 11, 9 to 11. So it has a much more variance. So the readings of B are actually less precise, but because they are closer to 10, they are more accurate. So B is more accurate than A and A is more precise than B. Okay. So this is one simple example to see. If all of the values are very closely banded, then it is more precise. And if they are closely banded to the let's say real value like this, then this is both accurate and precise. Okay. Yeah. Next we looked at where you need a dynamic measurement type sensor compared to a static measurement type sensor. So the vibration of an engine actually has much more varying properties. So you need a dynamic measurement type sensor. Next we looked at the natural frequency of the transducer and the cases where you can use such kind of transducer and where you shouldn't. So we saw that if the natural frequency, you should avoid measurements where you can expect your frequencies closer to the natural frequency of the transducer. Okay. So here the transducer's natural frequency is 1 kilohertz. So when you are measuring, you should make sure that whatever you are measuring should be far away from the 1 kilohertz, or you should choose a transducer such that it is far away from the signals which you are frequency of the signals which you are measuring. Okay. And you should basically avoid the resonance between the input and the output of the transducer. Next we look at the dynamic range, how to determine the dynamic range given the signal amplitude and the resolution. So the dynamic range is related to the range and resolution as 20 times log 10 of range by resolution. So if you know the resolution and range, you can calculate the dynamic range. Next, we looked at one more case for calculation of dynamic range, where range and resolution are not given, but the type of storage system is given. So we know that type of storage is actually related to the range and resolution, as resolution is equal to range by 2 power n. So from that we got the ratio of range and resolution, and from that we estimated the dynamic range. Okay. Next we looked at some different kinds of sensors and where which will be useful and some questions on that. So one of them is, what are the units for charge sensitivity for an accelerometer? So as it is given charge, so you should look at the units for charge. So in this case it's picocoulombs, and for acceleration meter per second square. So coulombs per acceleration, picocoulombs for meter per second square. Then we looked at what is the instrument that is used to display the voltage as a function of time. So oscilloscope is actually used for that, and it's not amplifier or transducer. It's called oscilloscope. Then we saw what sensors can be used for measuring displacement. So all the three mentioned here, the LVDT sensor, eddy current principle based proximity probe, and capacitive probe. All these three can be used for measuring displacement. But eddy current and capacitive, you can only use it for metal based objects, because they work, eddy current principle works on based on generating eddy currents in metallic objects, and capacitive probe also works only for metals, as it depends on the capacitance between two plates. Next we saw where piezoelectric crystals can be, and for what exactly piezoelectric crystals are actually used for. So they can be used for measuring both acceleration and force. The way they are set up is different, but the main material is made up of the piezoelectric crystal. And then photo or optical tachometer is actually used to measure the rotational speed. Next we saw the principle of stroboscope and how you can use it to measure the rotational speed. So it works based on if the frequency of on and off of the xenon lamp matches the rotational speed RPM frequency, then it looks like stationary. Then the object which is actually rotating looks like stationary. So based on this principle, you can actually measure the rotational speed. Next, we looked at what are the following can be used to measure temperature. We saw that thermocouple, RTD, pyrometer, and thermal cameras, IR thermal cameras, all of them can be used. But the pyrometer and thermal camera are non-contact based, so they are mostly used in high temperature cases, as the resistance based and thermocouple based might fail at very high temperature cases, so we use non-contact based ones. So we also see that the sensor which can be used to measure both AC and DC currents, which is the Hall effect sensor, and inductive current sensor works on the induction, which is only true for AC current, so it only works for AC current. But Hall effect sensor works on the principle of current generation due to changing magnetic fields, or the it in turn actually the changing current actually also creates magnetic field, so both are interrelated. So Because of that, it can measure both AC and DC currents. Next we saw if you want to get the composition of the chemical elements, which one you should use, whether atomic emission spectrophotometer or atomic absorption spectrophotometer. We saw that atomic emission, it will only give you a qualitatively tells whether if a chemical is present or not. But if you want to know how much of it is present, you need to do the atomic absorption spectrophotometer. And it will give you the how much of a chemical is present or the exact composition of the chemical. Next we saw that which one is better for measuring acceleration at higher temperatures, a piezoelectric based one or a strain gauge based accelerometer. We saw that piezoelectric is made up of ceramics, so they can easily withstand very high temperatures. So they are suggested for measurements at higher temperatures. Okay, yeah, that is it. Does anyone have any doubts? Question number 6. Yeah, the dynamic range. Yeah, decibels, dB. We just that's it. It's not like volts or millivolts or anything. It's just decibels because we are looking at the ratios. Yeah, yeah. Range by resolution. Yeah, yeah. Anything else? Okay. If no other doubts, you can log out. Thank you. Mostly we won't have the session on next Saturday. We will have it on Monday. You will receive an email regarding that if you haven't already received. I won't be available on Saturday, so I will take the session on Monday.